Good morning. Welcome to today's technical webinar sponsored by NT-MDT. Today we have Dr. Sergey Maganov presenting challenges and solutions in practical atomic force microscopy. Sergey Maganov almost needs no introduction based on his wide contributions to the field of AFM. Sergey graduated with a PhD in physics and mathematics from the Moscow Institute of Physics and Technology. He has held positions at the University of Freiburg, Digital Instruments, Vico, Agilent Technologies, and now is CEO of NT-MDT Development, an R&D subsidiary of NT-MDT that was established in 2011 for the development of novel experimental and applications capabilities of NT-MDT microscopes. Sergey has published over 200 peer-reviewed papers, 15 book chapters, presented over 200 seminars and 100 invited lectures, as well as authoring 5 patents in the field of AFM. So now, without further ado, here's Dr. Sergey Maganov to present challenges and solutions in practical atomic force microscopy. Sergey?
Thank you, Craig. Good morning or good evening for somebody who is now listening to our broadcast, and it's really my pleasure to start this webinar. And I just want to say a couple of words that this webinar is the first which we broadcast from the NT-MDT development office in Arizona, and this will be more or less general overview type of the webinar, and in the future we will go for more specific topics, and I think we will try to bring everything new we developed and find here. This particular seminar is named as a challenges and solution because that's what we meeting every day when we start to work with the atomic force microscope, try to examine samples of interest. The outline of the talk is now on your slide, and I try to overview really the broad application area of the atomic force microscopy, and will touch, besides the high-resolution visualization of surfaces, also the issues related with the local detection of the different material properties. I will start with some introduction showing what is atomic force microscopy today. When I was attracted to this scanning probe microscopy field in the end of 1980s, that was practically only scanning tunneling microscopy, and atomic force microscopy appeared as accessories to scanning tunneling microscope. But more than 20 years passed, and now atomic force microscopy is the dominant scanning probe microscopy techniques with variety of application. And this application, I just grouped that in several fields, and which we really will touch in our presentation. That's including the visualization of surface structures. This is primarily microscopic function of atomic force microscopy. Then we go to the probing of local mechanical and electric properties, and then even touch the issue, the combination of FM with spectroscopic modes. And in each field, besides getting information, like images or data is related to mechanics or electric properties, always people are thinking about how precise we do that, because now with the shrinkage of dimensions of the functional structures and also devices, people are more and more interested in quantitative measurements of materials properties on small scales. Therefore, that kind of different aspect looking at atomic force microscopy, because we want that to make also the quantitative as possible tool. But there are challenges, and we need to find proper solution to make this happen. I start with the theoretic backgrounds of atomic force microscopy because we found this is very useful in the understanding of the different issue of atomic force microscopy application. And this work based on our cooperation with another Sergei Dielectric, who was my colleague when I worked at Vico in 20s, and now I'm pleased that he has joined us in NT-MDT development, and we now continue working together in this field. Because he has a lot of theoretical knowledge and also practical implementation in LabVIEW software that, and we joined our efforts. He is from theoretical viewpoint, I'm from the application side to understand what's going on. And the result is that slide, which is show main issues. First of all, we consider the motion of the cantilever in atomic force microscopy using Euler-Bernoulli equation. There are a lot of different symbols here, but the main point that we consider this is really as a true structure, three-dimensional, without any approximation which simplify the problem. And plus, this is equation of the motion of the oscillating problem, because this is one of the main mode where the cantilever is bringing into oscillation by the piezo drive. Then the main solution, which described the dependence of properties of the cantilever, dynamic properties like amplitude, oscillation, phase, frequency, with the tip sample interactions, which are included here as the approach and retract, because also when the tip is coming to the surface and then coming back in oscillatory mode, the forces are changing, they can be different, so on. But the point is that by using the approach which is known as Krylov-Bogolyubov-Mitropolsky, which simplifies the solution of the problem of the three-dimensional motion, we can get the basic equations where we have the correlation between the cantilever properties and the force between tip and sample. And depending what kind of force, mechanical, electrostatic force, that gives us kind of mechanism to look at the basics of the interaction and how we can get describe the cantilever behavior, how we can extract information about tip sample interaction from the learning about the phase of the probe, about the change of the amplitude, and so on. That also basis gave us a chance to look on the different modes with more systematic view. For example, we'll be talking mostly today about the amplitude modulation mode. In this case, the equations are simplifying, and we have the relation between the phase amplitude, this set point amplitude, and the free amplitude, and this sinus and cosine, the RAP cantilever characteristic stiffness, the Q factor. But that was also important, the force model, the equation which describe the tip sample forces. And I will show you how we'll implement during the talk, but first I will tell you that this solution is implemented, and many of us probably have already the copy of the simulator based on the solution of this equation, which in principle can give you the means for modeling the images and the force curve on atomic force microscopy. This is one of these results which obtained with this simulator, which showing very simple thing. If you have the object on the surfaces as a small spheres of the, let's say, of the same size, but they have very different mechanical properties. And they also position a different spacing between each other. In the bottom row, they can kind of continuous sequence of these small spheres or balls. Now we can look how these balls appeared in the AFM images, because what we get in the image is still images. It's representation of the real world, but with the contribution of the tip, and the contribution of tip sample force interaction can change something. Therefore, we shouldn't be fooled by the images, because to extract the true quantitative information from the images is not as simple as you can. But that's what we need to do in many cases. Here, the example showing that this is the simulation done with the tip, and here set point amplitude 20 nanometers. We also took the free amplitude 20 nanometers. That means this is minimal tip sample force interaction in amplitude modulation mode, and this is the radius of a tip. Practically, this is 1 atomic radius for a single atom, which is also kind of ideal case, which never happened in practice. Typically, what's going on, if you still keep the forces very low but increase your tip size, then you see the picture is changing. And there are some things which is still good. For example, spacing between these spheres, because it doesn't change much if you go from this image to this, but the size of individual spot is changing. That's what show what you can expect, and I will show you one practical examples where this was realized to the studies of single molecules on the surfaces. Plus, on the bottom slides, you see we change also not only the tip size, we change in the force by putting set point amplitude half of the free amplitude. And in this case, what we see that here actually with the increase of the force, and having the same radius, let's say compare this image and this, the increase of force make your structures apparently smaller than some of them as you see here. But you see that with the force you start to see the effects related to the stiffness of the individual spheres. And here you see this is the stiff on the left, they are deformed less, and then the small spheres on the right more deformed, and that becomes more complicated profile, which does not reflect topography anymore. This is a mixture of the topographical and local mechanical features. That's one example. The second example, the force curve. What we do in the amplitude modulation curve, or if you want intermittent contact mode or tapping mode, there's different names for the same actually actions where we use the drop of the amplitude of the oscillating probe as a measure of tip sample interactions. Here I present you two cases where the calculation amplitude versus distance curve. It means as we far from the surface approaching, then tips start to interact with the surface, amplitude start to drop. Also, we can look what's happening with the phase in this situation, and the top is the calculation done for the conservative case. There is no any energy dissipation. Here, what you see that when we solve the solution, there are three possible solutions for that, and you see, therefore, a system can be confused on what solution is practically realized. There is the dotted here. There are also the solid, and then was thin line here. They all related to the different solution, which is dotted. Let's say it's low frequency, low amplitude branch. There are solid is a high frequency branch, and then the thin one is unstable branch. That case, conservative, you see that there can be different solutions, and the system can jump from one state to another. And if the situation doesn't change much or looks quite similar, if you include even dissipation in the case of adhesive avalanche was done on the bottom. But practical curves, which you see in the middle, they also show that the life actually goes more or less along these theoretical predictions, that we have the drop of the amplitude with the kink here, where the possible transfer between two branches here. And if you measure this kink with your images, you sometimes see the amplitude jump. There are some jumps of amplitude or the phase, because here also you see there is a jump from, let's say, attractive interactions also you can say, because this was below the zero level, and then you go to repulsive interactions. And in this case, if you stay at set point conditions where that happen, in images you can have patches of different contrast, which you can be confused with. But this is really shows that the life going, and this is phenomenon is known as a bifurcation, the transition from different branches. And you see unstable branches is not realized, but here we have more, this is large amplitude branch, and then there are, this is small amplitude, typically attractive force interactions. That means we can learn from that a lot about our behavior and also bring us understanding to the things which we see in our experimental data. Now I will go to high resolution imaging. Here we also get help from the simulation, and I will show you how. First of all, everybody knows that life started with attraction that AFM, in particular in the contact mode, which was the primary AFM mode at the beginning. People can see single atoms. Actually, there was not atoms, there was lattices of layered materials which has smooth atomic flat surfaces. And that happened for many materials, and typical examples either graphite or tungsten, selenide or mica. In this case, what we get periodical hexagonal lattices, people using some filtering to improve the seeing the lattice. And lattice in general reflect the crystallographic lattice of the surfaces with a lot of variation, of course, because the size of that, as you see on the bottom, this is just pictures showing atomic structure of these surfaces. And it's much easier, of course, to look to get the corrugation on the mica. Is much more difficult to get on the graphite. That's the selenide somewhere in between. Also, the corrugations is smaller in the graphite, larger in the mica, and then with all this corrugation of atomic scale level, and therefore you need to have very good instrument with low noise and mechanical and vibrational stability to get this picture. But that's what's easy that people generally can get with many homemade and commercial instruments. Situation become difficult when you start to talk about the molecular lattice and amplitude modulation. And up to now, there are a few groups where people reach that resolution, imaging the lattices, also images the lattices with defects, which people believe that demonstration of true atomic resolution. That's done in a few laboratories, and I probably emphasize the Professor Yamada laboratory in Kyoto University, where they've done a lot of that in the amplitude modulation and also frequency modulation mode. What with a commercial instrument is not yet a routine procedure, and that's, I think, I hope it will happen shortly, and we also doing now a lot to improve this resolution, and I hope in the nearest future we can show the progress in this field. But here I took my old data, which done in 2004 on the left side, with the dimension 5000 instrument, which does not exist anymore. But I wonder that I think at the moment all commercial instruments cannot repeat the quality of the results obtained with the amplitude modulation mode on this machine. And that reason was it has extremely low thermal drift. Therefore, if you losing on sensitivity or you're losing on the signal to noise ratio, you can get help from the low thermal drift because you can scan slower. And these images were done with scanning rates around 1 Hertz, even on very small stage. This is only possible when the drift is extremely low. Yes, we can get images, we can get defects, which is evidence. Now the question was, do we learn much from that? And this is again in simulation, which the work we published with Sergei Velikov somewhere in 2006, we show that simulations show that the true atomic resolution on the lattices, and this is, we take this polydiode stellene crystal, which we get a lot of these images. This is structure expected. We construct based on crystallographic structure the model of this of the surface, and done imaging with different conditions. And what we get that only the true picture, absolutely true picture we get where tip is of atomic size, and the amplitude is very close to the amplitude of free oscillation. Means there is practically no tip sample forces interacting. When you start increase the force and tip size and coming to some kind of situation at the bottom right where is more or less realistic in the practical application, what we see, you see that we still see these two defects, which are especially introduced in the latest, but the latest already is very different from expected one or from real one, because a lot of the convolution effect happened here, periodical, particularly related to bifurcations, also because there are several solutions of the equations where you go in the periodical structure with your tip, where dimensions comparable with the latest dimension. Therefore, still at the moment, I don't think we achieve true resolution, atomic resolution with IFM. To do so, we need to go to lower forces at the sharper tips and make instruments which can perform at these conditions. However, getting these lattices is a good demonstration of the general performance of the instrument. Okay, let's move further and get a little bit positive on the imaging of high-resolution imaging, and say that this is what example I encourage to look everyone who has microscope, because you can serve these two purposes. This is the images of the normal alkane on graphite. These samples can be easily prepared from the alkane of different lengths, and then they form lamellar structures which lie flat on the surface, and the distance between them is consistent with the length of this chain, plus what you can learn, because you know that all scanners need to be calibrated, and calibration is tedious but necessary part of the experiments, because you want to get right numbers from your measurements. Therefore, that you should do systematically, but how to do it in small scales? There is no man-made standards for that, and the alkanes in some sense can substitute that, because the spacing here, for example, C36 as 4.5, and you see the strips, lamellar edges, what you see here, they here, plus if you do it very carefully, then you can see the single layers of two molecules, and the molecules around 5 angstrom in kind of in diameter, in thickness. Therefore, this step which you see also will be good for the calibration purposes. Of course, you can try even to do C18, and this is done with all imaging. Now we can do it with Integra Prima, and we can do it also with Solver 336, for example, images to get this resolution. And you see that this is kind of 100 and 150 nanometer ranges is a really good demonstration of the high performance of your instrument in the way imaging demands really high resolution. Now we will go further on. When the single molecule, that's we coming to this situation I explained a little bit earlier. That's practical case. This is fibrinogen proteins, single molecules on the microsurface. You know that TM showed that there are 3 balls, individual proteins. There are some related models. With your dull tips, you indeed see this kind of combination of the balls. And if you take dimension of this individual molecule, fibrinogen, from that, you see that the IFM image, if we show true structure, true crystalline, true structure derived from crystalline measurements, then you should see this kind of image. And that's what's possible only with atomic size tip. However, if you do realistic tip, then there looks like more balls, and this is actually consistent with what we see in many pictures. In some pictures, however, we can get even higher resolution result details of that balls, but that's not, that demand a really sharp tip. But more realistic tips, we have this. But this is also, simulations show that this is a realistic representation of the molecules on the surface. We actually were checking the conformation of that molecules. But the increase of the size of that molecules is due to the tip convolution. Now we go further and we go to more bigger structures, let's say coming from a few nanometer to 10, 20 nanometer range. And this is, I took some examples of the polymer morphology. The point is that here the morphology relatively smooth, and then you see a lot of details. For example, if you take this spherulite, it's smooth, but it's corrugated, but there is no much kind of local corrugation. It's just the surface, let's say, of the ball here, 1.2 micron or 55 microns, and this is a spherulite. You can easily look on the structures, go zoom and distinguish the lamella organization in these beams of the structures. You see there are platelets here. These platelets around 10, 20 nanometer, depending on the polymer. In other polymers, you can find, for example, in HDPE, high-density polyethylene, the morphology nanostructure become more peculiar, and you see a lot of these shish kebab structures which are formed by alternation of the fibrilla and lamella structures on the fibrilla. And that shows you that you really can get a lot of these details with the relatively high resolution. But these surfaces, at small scale, are pretty smooth, and that's easy. Actually, the AFM is the best when the sample is very smooth. But however, our life is different. We need to look also on samples which might be not very smooth, and this is a couple of examples. Here, this is extreme. For example, extreme is looking at microporous nitrocellulose membrane of one type where the holes on this structure make really the elevations and the depressions very high. This is a 4 micron. And if you imagine the size of the tip is around between 8 to 10 micron, that means you really need to have a very high aspect ratio tip not to touch the structures, especially in the holes, by the side of the tip. Unfortunately, that's happened, and this is now the tip limitation. Even if you do other type of nitrocellulose membrane is not as kind of not corrugated as this extreme one. Here there are corrugation, let's say, around slightly less than half a micron. Here you see if you image with irregular tips, which has opening 35 degrees, so you can often have this kind of artifacts. You see the structures lean on one side and they kind of repeats itself, and that is to the convolution of the tip with this material, with the structure which has these holes. If you have the tip much sharper, and you can find different manufacturers the tips with opening as sharp as 9 to 10 degrees, then you can easily show the topography which reflects the structure much more truthfully. Therefore, imaging of topography is still very important, very informative, and can be very challenging task where you need to optimize your imaging conditions, you need to optimize your probe in order to get true, reliable information. And it comes not only on the large corrugation, even in small corrugation. I come on corrugation 10 times smaller. This is a cell guard. This is the image of the microporous polypropylene membrane, 240. In this case, there are lamellar regions and fibrillar regions alternate in this material, and the spacing between the fibrils is actually the pores where which used as a filter. Some molecules go, because of the small size, they go through this membrane, the other not. Now, here is important, a lot of people showing high let's say fast scanning images on this membrane, and you see that they tear apart the structure by fast running tips, and then you see the kind of increasing holes in between, which structure created by the tip. It's not realistic one, and you can be fooled by that situation, because in order to profile that, even on the corrugation of 40 nanometers, you should have a very proper adjusted scan rate, feedbacks, and amplifications in order to get truthful information. You should always watch trace retrace contours to see that you are really do it very gently and not disturbing the structure. Of course, zooming out after the imaging some local region also help to verify you are not destroying the structure. Also, we recently looked on very small object of the same, let's say 40 nanometer corrugation. This is not polymer. This is epitaxially grown silicon germanium crystals here, and they have, because the crystals have pits, they're not so deep, but again, they have very sharp edges, because this is crystalline structure. And our experience that using the regular tips, we have much less corrugation compared to the high aspect ratio tip. That means you really need to watch the situation also on the materials where corrugation, let's say in tens of nanometers, not hundreds of nanometers. In the tens nanometer range, you can have this problem, and you need to optimize your tip. Now we will switch from the high-resolution imaging for the visualization of surface structure a little bit to compositional imaging or compositional mapping, and first with the phase imaging. Here, typical polymer, and polymer polydiethyl siloxane spread on the surface. There are patches where tips see the substrate, then inside of polymer, you see there are regions of different contrast, and phase differentiate them. You see, phase give you the compositional map. Height show you some corrugations, but phase gives you the information. There are three components in this object. There are the location where tip interact with the surface. There are regions where interact with amorphous polymer, and the interaction, this is patches, bright amorphous, and the dark is where interact with lamellar structures, which are more rigid, but this rigidity is kind of intermediate between the very rigid silicon substrate and very soft polymer. Now what I want to, this is what kind of assignment given here. Here I want to notice that different instruments, the way how people represent the phase can be different. Therefore, in NT-MDT instruments, actually the bright color in the phase images, which is done at elevated forces, where you go to repulsive interaction range, bright color is corresponding typically to softer materials, and a darker color to the stiffer one. Let's say in the instruments I work in the past, in the digital instruments /Ripa/ Bruker, they different contrast variation, because the phase is kind of used different during the tuning. In one case, it goes through the zero from high to low numbers, another case, vice versa. But this doesn't matter. With the phase, the problem is that you could not understand it. It's really good measure of the differences of materials, but to convert that to the numbers, people didn't succeed for the last 20 years, and I doubt they can do it, finally, because the phase is like a staining agent in the electron microscopy. It shows you differences, but quantification extremely, extremely difficult, if possible at all. Now, I will go more examples showing that we can do it on the different systems with different resolution using the phase imaging. This is like classical examples you can find in many publications. Then you can, in many ways, for example, if you have blend of two polymers, LLDPE and polystyrene, and plus LLDPE, because it's crystalline polymer, it has lamellas, and you see lamellas in the phased image. Clearly, these dark strips in the bright amorphous matrix, that's clear indication that this bright patches belongs to LLDPE, where polystyrene is more harder one, it's darker in the phase, plus you see there are small domains of LDPE just embedded in the big island of polystyrene. That's help you to understand, help you to see the distribution of components. The life is so now that people usually make materials from multi-component systems. There are they're mixing polymers with some inorganic fillers and so on. So people want to see the compositional map of this material, see how one component distributed in the other, because this finally reflects the properties of the materials there, and that's what many manufacturers try to achieve to improve mixing, to specify morphology to the particular practical task. We can also see that on the smaller structures like strip block copolymer, in this case, the important point in optimization that if you do very low imaging, low force imaging, then here you see the topographical features, a little bit of noise because you try to stay a really very low force regime. Phase doesn't react at all. Then if you change your set point lower, and then how much lower depends what your tip stiffness, depends what material, but lower what typically you start to see the different picture. And you see here that structure doesn't reflect topography at all. Again, it's mixture of the topography and mechanical, local mechanical characteristics, because see here, phase now shows amazingly high contrast of different component and polystyrene blocks. Most likely this is darker stiffer, which goes to stiffer component compared to polypropylene. Again, if you drop your force back, you see that because here the rubbery layer is the rubbery component is dominating the top layer, means your tip deformation, they are not irreversible. The rubber recover back, and if you lower the force again, and you see very nice, see the very nice topography without phase. You can scan back and you see that place, if you haven't done much force interaction, they will completely recover. In some cases, if you've done excessive force, there will be some damage area. That means you disturb the surface layer. Now we can go further on, because so far we are talking about the kind of qualitative mapping, compositional mapping, when we see the different components on differences of their local properties, which is combination mechanical and adhesion properties, but how to extract the number. So far there is nothing better than just another indentation. You can understand another indentation, not necessarily the process you only make the holes. Also, in many cases, you deform elastically and then material recover. It's also not an indentation, but that doesn't leave the marks. However, and you can do it in different modes. You can do it in contact mode. You can do it in amplitude modulation mode. You can do it in the peak force mode. In most cases, you are deforming material, and what people are extracting, they want to extract the force versus distance curve, then to analyze that and get the idea about the quantitative elastic modulus or adhesion. That means in order to do that, you need to record force curve. That's what conventional wisdom, and then analyze this force. That sounds simple, and that's absolutely not true. Because what you need to take into account, you need to take into account many things. And that's what is listed here. First, you need, of course, have a very good knowledge about probe itself, tip shape, apex size, spring constant. That you need to spend time to do that, because no one of manufacturer will give you correct numbers of that. They will give you some approximate number, and then that means you can do experiments with approximate quality. But if you want to do that, you need to learn that yourself. Plus, you need to record these curves. That's maybe not difficult, but you should have into your mind that you can do it at different level of the force. And your penetration in material can be reversible, can be irreversible, can be plasticity, and so on. That means you need to know, and depending how deep your penetration, that defines what type of model you need to apply to extract the numbers. Also, it's important in many cases to record if there are some indentation marks left, because this is a indentation of the form of the of type of deformation you've done to the sample. Then you need also from these curves, you need to convert to the force versus penetration curves through the optical sensitivity calibration, and then choose, finally, when you have done all this, you need to choose the appropriate model for extracting the mechanical and adhesive data. This is examples I will show you done on low density polyethylene. You see, we intentionally left the marks, you see, but here there is no pileups. This is one type. In some materials you will see there are bright features around. That means pileups. You push material. There is a lot of plasticity in this case of material, plastic deformation. Here we've just done that. However, what you see, this is after you've done the process. When you're doing the process, this is a force curve. You see the tip on the way back left here. And there are some distances here, probably around 200 nanometers. When we measure the left hour marks, they are only 100 nanometers. That means between the process we done and the image we get, material recover half of its deformation. That showing that there is really this is not elastic process. There are little components related to the viscoelastic response. However, all these formulas, which are listed here, they stay in the case where people assume that the deformation is conservative. There is no energy dissipation in that. It means truly saying you can only in first approximation do that. But to understand that, to get dissipative and viscoelastic deformation, we need really to do that carefully. We need to spend more time to work on the better models to describe that and get numbers. In literature, again, we've been involved in this nanomechanical business earlier, and there are some publications. There are some success if you stay in elastic deformation region for different material. You see trace, retrace coinciding. Then, and also material is homogeneous, I'm sorry. Then in this case, you can get the numbers of elastic models and work of adhesion, which are realistic. They correlate with the theoretic predictions and also with microscopical data. That happen, and that there is a light in the end of the tunnel, but in more realistic situation where you have semi-crystalline, for example, material, where you have composite material. And this is most interesting because what people are worried about strengths of materials on interfaces. On interfaces, very small regions of material between two phases. That where only IFM can bring tip to this location and make it then. But how to get this information quantitative by mechanical properties is still an open question. And again, that's our office here in Arizona was created to dig in this problem. Yes, well, this is one of the issues we are working on, having in mind that we have all this mathematical apparatus for treatment of the data. In the spatial cases, we need to go further and consider more complicated situation. Now I'm switch gears to electric modes. Again, this is very tricky general situation. Of course, I like to deliver you the latest and the best, but I will restrict myself only on some general description of this field because we are thinking within a month or two prepare a more defined, more specialized webinar about the multi-frequency measurements in AFM, in particular with emphasis on electric modes. Here I just describe because this part of this what can be done even with the traditional microscopy where people are using Kelvin force microscopy and capacitance measurements to get the electric and dielectric properties of material. Typically, the situation in measuring electric response of the surface is related with or described by the models where people are considering the capacitance-like settings, where the electrostatic force interacting between the tip, usually it's conductive probe, and the samples put on the back electrode. The sample can be conductive by itself. And then what we do, we measure electrostatic force, and then with additional simulation of the force on different frequencies and using also the DC offsets, we can really learn about dependence electrostatic force on the applied voltages at different frequencies in DC component. Also, which is the force will be related to the difference of surface potential between tip and material. And because of square dependence and for capacitance-like settings, we have several components of the force at different frequencies, or we call it electric frequency. It means that's typically different from the frequency we use for the imaging in intermittent contact mode or in AM mode. Then you see we can, by nullifying the force on the omega, we can get the we can just finding the offset which equal the surface potential. We can do Kelvin force microscopy. We can measure DC-DC component. If you look on the to omega response in DC-DC related to the electric permittivity, and I put a few words about that. Now what we do, I will not describe single pass approach. You can read it in some literature, but we want to devote special seminar on that. But I will take you some results and a show on some standard materials we use. And this will be fluoroalkanes. We have a strong dipole moment and fluorinated part on junction, also maybe at the end of the CF3 groups here. They form different structure depending on the substrate. The dipole moment and fluorinated part is strong. We're going to also look on these structures. We'll look also on blends of polystyrene, polyvinyl acetate, because they have very different behavior. They have different sex potential there. There are also dielectric properties is of interest. And that's, I will show you a few results on that. Just extract the main results. You see, we can, in principle, go into the multi-frequency measurements. We can get simultaneously height, mechanical phase. You see, we do really low force, and this is very important because if we want to deconvolute mechanical electric interaction, we really need to do imaging very careful, with very small forces, not to disturb, not to complicate the situation. Simultaneously measured surface potential show that there is strong potential on these fluoroalkane aggregates, which are related, described by this model. There are the molecules standing up and preferential orientation of the dipole moment vertical, therefore gives you up to 1 volt difference between surface potential of the surrounding material which deposit on silicon and that kind of domains. You see contamination particles don't see surface potential, but of course this is material which is in tip sample junction. You can see it in amplitude cosine theta. This is actually alternative on the DC-DC measurements. On the to omega, and in case of the phase modulation. But here I will not go in detail, but because it's related to electric properties of material, you see this, any material will be seen inside the tip sample junction, and this is contrast is very different. That where molecules standing on a graphite, the same molecule lie preferentially, and then what you see here that the height and the surface potential looks very different, and the patches of the substrate here seen as a bright one. Also, if you go on that regions which has very fine structure, you can go down to 80 nanometer. Here around 6 nanometer spacing between the lamellas of fluoroalkanes. Here they partially interdigitated. Also we see the traces of surface potential. And here we get the idea from images about special resolution we can achieve in measurement of the surface potential. Also with sensitivity. You see this is traces here. This is trace of the surface potential. It's noisy, but you see this only 50 millivolts dimension. Therefore, I think we can really measure around 20 millivolts, sometimes 10 millivolts. That can be improved. You have dollar tips, because with dollar tips, electric signal is improving. However, the resolution special will be deteriorated a little bit. But here, the special resolution done with sharp tip, conductive tips, you see we can say about probably a couple of nanometer resolution, because this is 80 by 80, and you see these very small strips in both images in height and in the surface potential. Now, of course, a lot of people still use lift mode. And lift mode, which is done when in the system when you don't have a possibility to measure different frequencies, to do single pass, you measure the same frequency but separate mechanical interaction with the electrostatic interaction, making the experiment in two passes. First you learn about the profile of the surface, then you remove tip, and it's recommended to remove up on this from the surface and just measure the electrostatic interaction with the remote tip. But of course you start to lose on sensitivity and resolution when you take tip away from the sample, and that's really reflected. We can do probably our instrument, the only one which you can do both modes now, two pass and single pass. Here what we have topography of the, again, fluoroalkanes. No, I'm sorry, this is a mistake. It's on mica. It's correct, mica. Now what we see that if you do in the two pass potential image, you see very weak contrast of this aggregates. You see, you can improve that going to the negative lift. You can do it on smooth surface. You cannot do it on the rough surfaces. But with negative lift, you're improving the contrast. You're going practically here the amplitude was around 50 nanometers, and this minus 40 nanometers. You really approach with the tip to the bottom or very close to the surface. Still. Here profile, if you take here profile, this is more smoother and less corrugated than the profile measure in the KFM-PM regime, which has more strong and more related, reflecting the strong surface potential of the structure, more correct numbers. And you see it has more features. It means the spatial resolution also is higher on this pass in this image, and you see that here. It's you can see by your eye, but that's showing that that is the many cases can be the method of choice if you want to do surface potential measurements. But again, here we come to this optimization, because I will tell there are different type of challenges now if you do to multi-frequency measurements, because you have usually several different detection schemes to do to measure the same property. Now the problem is, for the particular material, you don't know what will work the best, because that's kind of open question. Because if you take SRAM structures, and that's semiconductor structure where there are different doping regions of different type and different concentration, just to make the active devices from that structure. So you see the comparison, the height and surface potential image show that there is no direct correlation between that. For example, this is two different regions, and they don't see here as a different. And they really topography surface potential is here. There is no any cross talk about that, or people sometimes seem afraid of that. But look here done in a very different KFM ambient modulation mode, because as a phase modulation mode we use for the smooth surfaces, this is rather corrugated. It doesn't work here. That means, yes, unfortunately, we cannot look at all the structures in the world, but this is our users should really have the idea that the optimization in many cases on their shoulders. because that difficulty of multi-frequency measurements, you have more opportunities and more challenges to get a really good job. But as here also I will show that even on the metal samples where the difference of work function is reflected in surface potential images, you can do the job, you can do compositional mapping if you want. The trick about compositional mapping with the phase imagings and with mechanical and adhesive properties, that's mostly related to studies of soft materials with modules less than, let's say, 10.7 gigapascal. For hard materials, there is no way that you mechanically can get compositional maps on the same systems like metals, but use the electric modes gives you broader capabilities in studying the composition in the hard materials where the components is not soft and mechanical changes will be not noticeable. Now the last part, last maybe 5 minutes, not more, I will talk about the local dielectric measurements and the way how people trying to find the way to the dielectric microscopy on the very small scales, because that's very important information on permittivity of the materials, and that characteristic is very complicated. It depends, and it's complex. You need to measure different frequencies and so on and so on. But that gives you a lot of information about, let's say, molecular motion in the system. Also in this slide, because we're looking on this system, polystyrene PVAC, it's microphase separated blend. The components don't like each other. PVAC supposedly in the domains in the polystyrene matrix. I say supposedly, now we know this true, especially when we start to use with Pavel Doroshkin group with spectra, integral spectra, the combination IFM with confocal Raman. And we learned that this materials has very distinctive scattering bands on different regions. We use that for mapping. This is the height, the same kind of morphology you see here, but here the maps in the individual bands which related to the component, and we see that indeed these domains are completely spherical domains enriched in the PVAC, and the matrix is polystyrene. You see here that PVAC regions, polyvinyl acetate, they have some kind of reasonable dipole moment, and polystyrene not, and therefore they give the patches which distinguish the surface potential. But the same areas with the same morphology in measurements of DC-DC and the electric response looks very different. And actually, they're even more complicated because in many cases it shows that this is inverse, kind of looks like inverse of the topography. And indeed, what we found, and that's a kind of known knowledge now, established knowledge, that in the case of surface potential, and we measure surface potential practically directly, if not taking into account the contamination of tip and the sample, but in many cases on the same material, these differences in the surface potential is a pretty good direct number. For example, in metals, we found that the difference of potential directly related to difference of work functions. That means it's direct measurements. Surface potential is probably the only one method related with IFM that have direct measurements. Case of DC-DC situation is very convoluted because it also depends on thickness of the material, which is in junction between two electrodes, let's say substrate and the tip. Therefore, you need to have extreme efforts to get the information from that. That's, again, we're using the same formula I showed at the beginning where relate the cosine theta. This is the phase changes as a function of the interacting force. In this case, you can consider this is the force electrostatic one. And Sergey, again, make a lot of efforts to get the proper analytical equation related to the response of 2 omega electric, which the electric response in general, how it's related to the parameters of the cantilever and parameters of the samples. And finally, another difficulty is that the capacitance of this tip sample junction with the material is related not only on the permittivity material but also on the thickness, and they are combined together. Therefore, you get that response just usually with very convoluted response, which include the thickness of material and epsilon of the particular component. However, there is the way to extract. Again, we use the LabVIEW-based program to get the numbers, and we've done these studies. First of all, on simple component, we take this component, make a thin films on the ITO glass, and then make a scratch with the toothpick, not to destroy the glass with the hard sharp stuff. We just sharpen it, a wooden toothpick, and make a scratch. And then this is a scratch, and we see that the measured dielectric response on this material, where one is polymer, one substrate here, polystyrene here, PVAC, and we measure a response at different voltages applied. You see that there are the increase because the square dependence is more or less, and the low voltages we have square dependence of the response as a function of the voltage reproduced. And based on Sergey calculation, we found out that there are different PVACs, and there are some ratio around 1.5 and 4 between the polystyrene and PVAC in the dielectric properties. And we build the model for more complicated structures, showing that despite the presence of the corrugated surface, we still can get the compositional map and can assign the different regions to the different materials. But this is much more difficult than in many other cases, but this is how the life arranged. And I'll finish you that showing that a lot of information I presented is actually confined to the set of the samples we developed through years. And this is kind of set of the samples which show that can be used to evaluate different modes. And we start to, inside the company, we made several sets to distribute, and people can try and can learn how to do the particular modes. And with that, I'm coming to conclusions. I was telling about several things, about the high-resolution imaging, that we still have a room to go further and to get to true atomic resolution, which this is my subjective view, but I believe we are not achieved yet. Then we need to look again and can do a lot of work on the mechanical properties and studies of the local mechanical properties, and go to the extreme special resolution situations, which other method really cannot do much. Also, I will talk that there are a lot of advances going on with electric measurements, dielectric measurements, and that's what will be this kind of pre-announcement of the following seminar, where we can put more emphasis on that, more emphasis how to optimize measurements. But in all these issues, still we have challenges. We're finding solutions. Are they ultimate or not? That's a very difficult question. I think we still have a lot of room. And of course, I appreciate my everyday cooperation with John Alexander. He's our electronic guru, Sergey Belikov, and Craig Wolf, who was presenting, moderating this event. And thank you very much for your attention. And I will be happy to answer as much question as possible now, but of course, we will give your answer all in written form afterwards. Thank you very much.
Thank you, Sergey, for a very interesting and insightful presentation. We have a question from the audience. They want to know, how can one measure real properties, topography, adhesion, dissipation, of soft samples like human cells in solution? The comment is, the main problem for normal imaging at high force should be applied so that you get a crisp, clear image. Low force leads to blurry imaging. How can one change? The distance on which the measured surface potential in single pass Kelvin.
Okay, that's okay. The imaging of the cells by itself, an imaging of the cells in the liquid, and then bringing the electric measurements to the liquid, they are all three different and very complicated problems. One thing, of course, everybody wants, and this is the privilege of AFM, to able to do studies in broad range of environments. However, liquid is the environment where make AFM work in the way we want is rather difficult. What we want, particularly if we go to the oscillatory technique, we want that we drive the cantilever in liquid, that we have only single frequency response, which was sharp. That means you can follow the changes of the amplitude and frequency nicely. That's both fail. Typically, the drive of the cantilever in liquid is very difficult, very, let's say, characterized with low Q. And there is no good liquid cell developed so far. There are efforts through magnetic drive, there are efforts through electric drive, but truly saying routine measurements is very, very difficult. Therefore, we need to have a lot of skills to do that. And that's challenge. That's outstanding problem. People for let's say 20 years, people haven't solved that. I don't know what even to say in this respect. However, still people imaging do a lot of mechanics. Of course, mechanics on soft materials is very difficult because sharp and stiff tips is not acceptable because you will penetrate and the cells and bring damage and so on. If I will start from the beginning, I will start to use relatively dull tips with the beads that we can look on them to evaluate the dimensions, because we need that to extract any quantitative information from deformation. We have a knowledge about that. One thing is, second thing that, of course, level of deformation is very different, and here you need to accept that. Of course, for imaging, you might need to go to very low forces for imaging of topography. If it's compositional imaging, because the cells also has kind of complex structure and can be regions more dense, more stiffer than, and so on. That you can do, but that's you can image when you're imaging at elevated forces to see these differences, and also from these elevated force measurements you probably can extract the distance, force versus distance curves to get to apply appropriate models. Are the Hertz model appropriate or DMT is appropriate? That again depends how you perform experiments. Maybe in very small indentations or very small depressions, you can describe that with just elastic / adhesive combination approach, but it's rather difficult. I haven't seen very reliable work on that issues, really. People try also to bring the electric measurements down to the liquids, and there are some couple of papers I'm aware about, but again, it's just at the beginning. It's tricky because again, if we apply the multi-frequency measurement, we need to have very well-defined spectrum, vibrational one of the cantilever in liquid. Then we can separate, let's say, mechanical and electrostatic interaction one just for purpose of imaging, another for purpose of the detecting the electric response. Unfortunately, we not started here in Arizona in our office this work on the liquids. We just looking on different accessories in the moment, and I hope I can within some time, let's say half a year, 1 year, I can get you more information about that. But this is, I will put imaging in liquid, imaging cells, and local properties studies, local properties as problem number 1 in IFM today.
Okay, Sergey. There's also a follow-up to the question about imaging cells in terms of peak force QNM. With that method, you can choose an appropriate frequency, and the comment is that good oscillations are not necessary. Can you comment on peak force QNM and its relation to these measurements, even though that's not a technique from NT-MDT?
Yeah, I understand, but that's peak force nothing different than the pulse force mode, which is kind of improved electronics, which gives some better capabilities of doing the measurements. And a basic idea about the pulse force was that to measure the force curves, limit number of the force curves to speed up the process of screening or mapping. And QNM, that was the topic we worked with Sergey Belikov and Bill Latvika, and that's actually elements of that analysis are implemented in the peak force software, particularly I think the MT approach. But you see, this imaging with peak force QNM is not free from these challenges I described in the presentation. You need to know the tip radius and shape. You need to know stiffness of that. You need to know the level of deformation you do for the mechanical measurements, because then, only then you can justify if you apply non-dissipative models to do that. And then you need to extract also the calibration curve, optical sensitivity, to get the true force versus distance curve. If you do this all 4 tasks, then you can rely on this data. However, you need to do that. You cannot rely on the data that provided by tip manufacturer. You cannot rely on specification of the tip shape by running the standard with the spikes, because you probably will shave your tip further. We get the strong feeling that the only way to get the true shape and dimension of the cantilever is go to the SEM or TEM. And then this is the QNM. Basic of QNM was, a big part of QNM was reconstruction of the tip shape from TM data. People are forgetting that QNM is not just getting the results, analyzing the formulas, but do a lot of preliminary work, which is actually justify the final results. If you're not done TM imaging and not done reconstruction of tip shape, didn't put the tip shape into this equation, which is in the basics of QNM analysis, then your error will be very, very huge, and I don't know if it will be well reproducible data as well. This is a challenge, and this doesn't apply. Is it peak force or pulse force? Is it a work with the force sensor, which just paper published by the guys from Stanford, where you don't need or is it harmonics approach? Anyway, because what you're generally talking, find a way to extract mechanical force curves from any type of the mechanical IFM experiments, and then analyze these force curves in terms of models taking into account tip and so on and so on. That basic is not, you're not escaping from doing this basic work. When you do this basic for any mode, including the peak force, will give you reliable data. But so far, I haven't seen strict, really, work which showing that that can be done. In principle, it can be done. Therefore, I will be happy to learn and to find out what is the best method to do that.
Okay, we have one last question from the audience, and then we're going to need to wrap up as we're about 20 minutes over time. The last question is, what's the best way to characterize the spring constant of the probe?
Okay, that's a good question, because this is again the part of this QMM process, and a lot of companies, and we including, we have the way to characterize the stiffness through the thermal tune, and this is procedures and routines already in the NT-MDT software. We have even 2 different ways to do that. We're getting very consistent numbers on soft probes. Doing the same for the stiff probes, let's say more than 10 Newton per meter, your error is increasing tremendously. And that's one of these challenges which we're facing. This is also the challenge of the KFM. There are some other methods which people use, optical interferometers, which can do this job better than AFM instruments because they are more suitable to this work. They don't need extra calibration of optical sensitivity. They have lasers which are focused on the tip better, but again, that's separate measurements. If you want to go and do experiments in AFM setup where you need to watch that your laser beam is really focused on the same spot of the cantilever when you do tuning, and you do that the beam is of the same size, and then you can get the reproducible data. But generally, that's a challenge, and I don't think on the for stiff cantilever we can get that 20% barrier eliminate. We cannot eliminate this 20% barrier for the stiff tips, and that's a challenge.
Thank you, Sergey. NT-MDT would like to thank all of you for taking time out of your busy schedules to attend our webinar today. We hope you found the topic interesting, the information useful, and we hope to see you again at a future NT-MDT webinar. Upon exiting the webinar, there'll be a short survey. It should take no more than 20 seconds to fill out, and the information would be very useful to us. And therefore, we would like to thank you all for attending, and have a great day or a great evening, depending upon your time zone. Thank you all very much.